Imagine that everything you know, stars, planets, galaxies, is only a small part of what fills the universe. Picture yourself drifting away from Earth, rising above the familiar landscapes, leaving behind our blue planet and venturing out, beyond solar systems, beyond galactic arms, through the vast darkness punctuated by distant lights. As you travel, the distances become immense, the structures sparse, and yet the expansion of space itself becomes apparent. You realize that what you're witnessing is more than just the movement of galaxies. It's the fabric of the cosmos stretching, quietly, inexorably. Around 70% of the universe is composed of something invisible, elusive, and still profoundly mysterious. We've given it a name: dark energy. It's not something we can touch or see directly, yet its influence shapes the destiny of all things. Galaxies, clusters, perhaps even the end of time itself. Until recently, scientists believed this enigmatic component to be unchanging, a constant presence in the cosmos. The idea was that this dark energy, once unleashed, would steadily accelerate the expansion of space, driving galaxies apart at ever-increasing speeds. This scenario became ingrained in our understanding of cosmology. The universe, we believed, would continue to expand, becoming ever larger, ever more diffuse. But now, new discoveries suggest that the picture may not be so simple. What if dark energy doesn't remain fixed? What if it evolves? What if the accelerating expansion we observe is only part of the story, and a deeper transformation is underway? Today we'll explore what this means, why this is one of the most compelling frontiers in modern cosmology, and how it could completely redefine our understanding of the universe's future. We will ask, what exactly is dark energy? How was it discovered? What have the largest galaxy surveys revealed? And what could this mean not only for science, but for the ultimate fate of the cosmos? Let us begin with a moment in time that changed everything. In the late 20th century, specifically in 1998, astronomers studying distant Type Ia supernovae made a dramatic and unexpected discovery. The expansion of the universe was not slowing down, as the force of gravity should suggest, but instead was accelerating. For decades, the assumption held that after the Big Bang, the universe expanded rapidly, then gradually decelerated under the pull of matter. But these supernovae told a different story. The distances between galaxies increased faster and faster, an astonishing result that set cosmology ablaze. To explain this acceleration, scientists introduced a new concept: dark energy. This hypothetical form of energy acts in opposition to gravity. Instead of pulling matter together, it pushes space apart. It is not visible in telescopes, not detectable in conventional experiments, yet its imprint on the large-scale structure and expansion of the universe is unmistakable. In the standard model of cosmology, known by the acronym lambda cold dark matter, dark energy is represented by the symbol lambda, the cosmological constant. In this framework, dark energy is treated as a uniform vacuum energy density filling space, permanent and unchanging. The beauty of the lambda CDM model lies in its simplicity and elegance. It provides a coherent structure that describes the cosmos from its earliest moments to its large-scale geometry and expansion. If dark energy is indeed constant and dominates the dynamics of the universe, then a profound prediction emerges. The universe will expand forever, at an ever-accelerating rate. Over cosmic timescales, galaxies will recede beyond our horizon, stars will burn out, matter will become ever sparser, and the cosmos will drift toward a cold, dilute future. Why does this matter? Because dark energy now constitutes around approximately 68 to 71% of the total energy mass content of the universe, according to the Standard Model. It is the major component, the dominant force shaping the universe's fate. If its nature is constant, we can make predictions about the long-term evolution of the cosmos. If it isn't, everything changes. This includes our understanding of gravity, of space and time, and of the ultimate destiny of all matter and energy. Yet, though we see the effect of dark energy, the accelerated expansion, we still don't know what it is. The source remains hidden, the mechanism unknown, and the basic nature elusive. We have glimpsed the consequence, but the cause lies beyond our present knowledge. And now we enter the era of large-scale cosmic surveys. One of the most ambitious efforts is the Dark Energy Spectroscopic Instrument, DESI. Over the course of several years, DESI has mapped nearly 15 million galaxies and quasars, producing a three-dimensional map of the universe that stretches over roughly 11 billion years of evolution. These data allow scientists to trace how the expansion of space and the influence of dark energy may have changed over cosmic time. By comparing the distribution of galaxies, the imprint of baryon acoustic oscillations (BAO), and observations of supernovae, researchers have begun to measure changes in the expansion rate and the relative strength of dark energy in different epochs of the universe. The results are surprising. They suggest that dark energy may not be as stable as previously thought. Specifically, the data from DESI show hints that dark energy's repulsive effect could be weakening over time. In a press release, scientists from University College London, UCL, noted, "If dark energy is constant, the universe will expand more and more quickly. If it evolves, the fate of the universe may be very different." The statistical significance of this finding sits around 4.2 sigma, not yet the gold standard of 5 sigma, but important enough to rouse significant interest and raise new questions. Why is this both alarming and exhilarating? Because if dark energy changes, then the lambda CDM model may not give the full picture. It might be incomplete or even incorrect in key aspects. Essentially, we may be on the verge of the biggest revision in cosmology in decades. The questions that arise are profound. What is controlling dark energy? Can it disappear or change in strength? And what does that mean for everything from galaxies to the structure of space-time itself? This isn't a sterile scientific detail. The implications ripple out to the fate of all existence. So now we come to the heart of the question. If dark energy is evolving, what does that entail? One possibility is that dark energy is not a constant vacuum energy, but a dynamic field, a changing entity that alters its density over time. A leading theoretical candidate is quintessence, a type of scalar field whose energy density slowly evolves as the universe ages. If such a field exists, the accelerating expansion we observe might be gradually giving way to new behavior. Another possibility is that gravity itself behaves differently at the largest scales. Perhaps our current theory, Einstein's general relativity, requires modification when applied to the universe as a whole. In this scenario, dark energy might reflect our incomplete understanding of gravity rather than a mysterious field. What do the data hint at? There is evidence that the equation of state parameter for dark energy, denoted W of Z, the ratio of pressure to density, may vary with redshift ZZ rather than remaining fixed at -1, the value corresponding to a true cosmological constant. Some studies interpret this variation as dark energy weakening over time, its repulsive effect diminishing as the universe expands. Now, considering different futures, if dark energy remains constant and strong, the universe will expand ever faster. Galaxies will vanish beyond visible reach. Stars will burn out. Ultimately, a scenario known as the Big Freeze awaits. If dark energy strengthens or drives expansion to extremes, the universe might end in a big rip, where expansion stretches space-time so violently that galaxies, stars, planets, and even atoms are torn apart. If dark energy weakens significantly, the expansion could slow, perhaps halt, or even reverse, leading to a big crunch or some other collapse or cyclical rebirth. This is no mere adjustment of a figure in an equation. It's a possible revolution in our understanding, from the earliest moments of the cosmos to its final destiny. We may come to realize that the universe is far more dynamic, far more subtle than the simplified models suggest. Why does all of this matter? Because dark energy represents one of the fundamental unknowns of the universe. If it is dynamic rather than constant, then our foundational models of space, time, matter, and energy may need to be rewritten. We could be at the threshold of new physics, new fields, new forces, new conceptual frameworks that alter our understanding of reality. What's next? The DESI project continues collecting data through at least 2026, targeting a final sample of around 50 million galaxies and quasars, offering even higher precision. At the same time, powerful space observatories such as Euclid, the Nancy Grace Roman Space Telescope, and the James Webb Space Telescope, JWST, will provide independent and complementary data about the cosmos, from its early epochs to large-scale structure. Today we have journeyed into one of the deepest mysteries of our cosmos, one that touches the very nature of existence. We asked, where are we located in the grand scale of the universe? Where are we heading? And will the universe continue to expand forever, or encounter a very different fate? The answer lies in dark energy, and in how deeply we can understand it. If dark energy is evolving, we could be on the cusp of discovering new physics, new forces, and deeper truths about reality itself. The future of the cosmos may not be a single, fixed path, but a panorama of possibilities. Subscribe if you're ready to explore this journey further with us. Leave a like if cosmic mysteries excite you. And in the comments, tell us, what do you think the future of the universe will be?